Hello everyone, welcome back to more videos. These are some of the last ones of the year, which is kind of exciting, kind of scary. We're kicking it back to first semester again, and we're gonna re-talk about some things we already learned, but in some more details. So this video is on solutions. And what a solution is, it is a homogeneous. So just remember, homogeneous means it's all mixed, it all looks the same. When you look at it like salt water, be an example, it's a homogeneous mixture. And it looks the same, but it can be separated physically. Separated physically. So you can evaporate something out, you can distill it out, and there's a lot of different processes. That's back to first semester. And what makes up a solution is the solute, which is the substance being dissolved. How many S's? Dissolved. Okay, sorry. And then the solvent, which is it's present in greater amounts, or it's the one doing the dissolving. So for instance, salt water, the solute would be salt, NaCl, and then the solvent would be water. Water is normally your solvent. In a lot of cases, it's a solvent. So soluble means a substance that dissolves in a solvent. So basically, if it can dissolve in whatever you're trying to dissolve it in, it is soluble. If it is insoluble, that means the substance does not dissolve in a solvent. So soluble, it does dissolve. Insoluble, it doesn't. That prefix in is a pretty good indicator. Now, if you have two liquids, you could say it's miscible. Oh goodness. So that's two liquids that are soluble in each other. So you can only say miscible if it's liquids. The liquids dissolve together, then it's miscible. If it's immiscible, maybe that's how you say it, I don't know. If it's immiscible, it's two liquids that are insoluble. So soluble, insoluble can be applied to anything. Miscible, immiscible is only for two liquids. And just remember, like dissolves like. Like dissolves like. So because of intermolecular forces, polar molecule is gonna bond with an inpolar. Polar will dissolve polar. Yeah. Okay. Okay. So how can we increase the rate of soluvation for solids and liquids? So how can we make substances dissolve faster? We can by agitation, so that would be shaking or stirring. And that allows for new collisions between the particles, and the more collisions you have is the faster it'll dissolve. You can also, by breaking the solute into smaller pieces, smaller chunks, it won't have, well, it'll have the same mass, but when it's smaller chunks to dissolve at a time, and that increases surface area. Oops, let's move it back. You can raise the temperature of the solute, which increases the kinetic energy of the particles, resulting in more frequent collisions. Because the aim of the game, to get things to dissolve faster, we want to increase amount of collisions between the particles. So that's how you make something dissolve faster. So for solubility, or actually, what is solubility? Solubility is the maximum amount of solute, the thing being dissolved, that will dissolve in a given amount of solvent at a given temperature and pressure. So solubility is how much salt can we get to dissolve in the water at a certain temperature and a certain pressure. So there's three things to describe this. You have an unsaturated solution. An unsaturated means more solute can be dissolved. You have saturated, which means no more solute can be dissolved. And then you have supersaturated, which is the actual technical term for it. And that means it's unstable in crystals would form. That's because more is dissolved than possible. Unstable. And that's just, say if you raise the temperature or something and you've got more to dissolve, and then you lowered it back down, and then now you have supersaturated because it can't be at that same temperature with that same amount. So really, if you think about these, maybe like a towel, if a towel's unsaturated, it's not wet, so it can still soak up more water. If it's saturated, it's already pretty wet and it's not going to do much to dry your floor. But if it's super saturated, it's like really, really wet and there's like water falling out of it. So maybe that'll help you remember it. I don't know. Okay, so here's some properties of solids and gases for solubility. So solids are more soluble, generally speaking, at higher temperatures. So if you have a solid, the higher the temperature, the more soluble it will be. So the dissolving for solids occurs quicker, more rapidly at higher temperatures, but the amount of solid that can be dissolved may increase or decrease with increasing temperature. So it'll dissolve quicker when you turn the heat up, but the amount will or can increase or decrease with increasing temperatures. So even though you might get it to dissolve quicker at a higher temperature, that doesn't necessarily mean you will get more to dissolve at a higher temperature. For gases are more soluble at low temperatures. And high pressure. If you think of carbonated beverages, that makes sense. To get the carbon dioxide to dissolve in the drink, they bottle it at low temperatures and they put it in that pressurized container. So that's why when you open it, you hear the hiss because you're letting all that pressure out that they got to get all that carbon dioxide in there. Low temp, high pressure. Okay, now we have these things called solubility curves. We all know my drawing skills, so I will not be drawing a solubility curve, but I'll kind of explain how it works. So what a solubility curve is it shows the dependence of solubility on temperature. And this is usually measured at grams of solute, so whatever you're dissolving, per 100 grams of solvent per your degrees Celsius. So what on earth does any of that mean? So let's draw a graph. Woo. So on our left, on our y-axis here, we're going to have our solvent. And this is normally going to be 100 grams of water is what it's going to be. On here is going to be temperature, because temperature always goes on the y-axis. So you're going to have numbers. Well, obviously, that's how graphs work. But you'll have numbers along the sides. And then you'll have a curve. And this will be, so say the graph will be, so say we have this thing, and then this line will be labeled with whatever element it is, element XY, or solute XY, so whatever was being dissolved in the water. And so what this shows you is at this temperature, and we'll call this say 30 degrees, and say this is 20 grams. This is at 30 degrees, 20 grams of this solute can be dissolved in this solvent. And also what we can tell from this curve is where is undersaturated, where's supersaturated, and where's saturated. So anything above the curve is going to be supersaturated. Anything under the curve is going to be unsaturated. Anything on the line, directly on the line, is going to be just normal saturated. So that's how you read these graphs. You're going to have the line or multiple lines, and you say ask a question like, it'll be some form of like, how much of this element blank can be dissolved at blank temperature in 100 degrees of water. So say, how much of solvent XY can be dissolved at 30 degrees in 100 grams of water. And we'll go to our graph, and we'll go up from 30 degrees, and we go across, and we see that 20 grams can be dissolved. So that's how you read the solubility curves. You can also do calculations with them because it's chemistry. There has to be math involved. So say it's asking, let's take this for example. The graph doesn't exactly look the same, but say at, so we have, I don't know how to draw. Okay, we're trying to figure out how saturated, or how much is dissolved at 90 degrees Celsius. And then it asks how much will come out if the temperature is decreased to 48 degrees. So you would have your graph. You'd go up to 90, you go here, 90 degrees. You'd go up. And on this graph, at 90 degrees, 45 grams can be dissolved in it. Well, now we're going to 48. So say here is 48. At 48, it's about 18 grams. So if we want to find out how much will come out, we subtract the starting temperature minus the finishing temperature to get 27 grams will come out of that solution. Okay, but these graphs are all with 100 grams of water. So what if we used 35? So same conditions, so we're going to start with our 27 grams that came out. Then we're going to times it. You're going to turn what that is into a decimal because it's going to be a proportion. So we have 27 grams at 100. Well, how many grams are we going to have at 350? And so, see, we would multiply these there, and then you see you have 27 times 350 equals 100x. So when you divide by 100, essentially you just be moving that decimal place. So you could do that also. You could work this equation or this one. They'll both should supposedly get you the same answer of 95 grams. There's a lot of different types of problems that can be done with this. It's a lot about knowing how to read a graph. So if you just remember temperatures along the x-axis, how much can be dissolved is along the y, and then you can just look at the line and match it up. So I hope this helps. If you have any questions, please feel free to ask me. Thank you so much.